Yeah. What I'm about to do is I'm going to repeat this, everything I just said. You can regard everything I've written here as scratch work. Scratch work, right? I just want you to see what the logic actually is. So now that I can see what's going on, now I'm able to articulate the actual argument, right? So the actual argument goes like this. Because multiplication is commutative, right? That is to say, A times B equals B times A. It follows then that the natural log of n multiplied by the natural log of 2 is equal to the natural log of 2 multiplied by the natural log of n. And that's true for all n. And because that's true, using the properties of exponents, it follows then that the natural log of 2 raised to the natural log of n is equal to the natural log of, looking at this one, n raised to this constant multiple power, ln2. And because these logs are equal, and the log is a one-to-one function, right, it follows then that 2 raised to the natural log of n is equal to n raised to the natural log of 2. And since that's true, if these are equal, then the reciprocals must also be equal. In other words, 1 over 2 raised to the natural log of n is equal to 1 over n raised to the natural log of 2. So, and that's what they gave us in the hint. So, yeah. And you know, when they give you a hint, it doesn't mean that you have to prove the hint. They're kind of giving you that for free. You know what I mean? But if I was in your shoes, I would be curious. You know what I mean? Like, because, yeah, I said it already. Like, at first glance, that wasn't obvious to me either. So that could be a useful trick to kind of keep in your back pocket, you know. It might come in handy someday. Well, let me put it this way. All right, let's use some things that we know. We know now that this diverges.
Right.
We know that this converges. Right? And one way of seeing that, right, is with the integral test.
Okay.
Because all these terms are positive, because they're decreasing, and it matches with and the sequence coincides with a continuous function called this one, we can look at the integral from 1 to infinity of 1 over x dx, right? And in this case, I could look at, I have in mind a different function. This is a continuous function. This is technically, that's a discrete function, right? You're only plugging in whole numbers. And so, in this case, I could throw the integral test at it. And whatever's going on here and here is going to answer the question as to what's going on up there and there, right? And what you find is if you go through the work, you'll see that this improper integral, the first step in evaluating this is to realize that this is a limit from 1 to b, right?
Like using t.
Yeah.
He's accepted.
Yeah, t works as well. But you take the antiderivative, right? And I'm not going to do the steps right now, okay? But if you go through the steps, what you're going to discover is that it's going to converge, okay? And it's going to equal a finite number. And because this limit exists, it follows that this series converges, right? But if you go through the motions here, and you evaluate this limit from 1 to b, what you're going to discover is that this one is not going to exist, okay? So all this is review, but what I wanted to show you that I haven't shown you before is just kind of a picture that ties these together. The picture that kind of suggests, why this might be true. So like on one hand, yeah, just the positive. I don't really need the negative side.
Well, so,
Uh-huh.
but then, okay, to me, the positive and the negative would reaffirm the fact that it does diverge.
Mm-hmm.
No, come on. But even still, we don't need to draw the negative side because the series, there's perfect.
If I was to superimpose, they almost look like the same graph, but they're not. If I was to superimpose the two, you would see that, close to the y-axis, this graph is taller than this graph. But close to the x-axis, this graph is low. It hugs the x-axis a lot closer than this one does, and these would intersect with each other at 1, 1, right? So they are different graphs, although they look pretty similar. But like when you evaluate, this series, the first term in this series is 1 over 1, right? And that could be represented as the area of this box right here. Because at 1, the height of this box is, I get that by plugging it into the function, and I can see that it's represented by this black box right here. The second term could be represented by plugging 2 into this function, getting a half, and then drawing a box right here, right? And likewise, at 3 I have a box, at 4 I have another box, right? And so the series is really the combined total of all those boxes. The integral rule says that although the area from 1 to infinity, it's not technically the same as this series, but the behavior is the same. The integral test is really giving me the region, right? Right here. This red region right here. Right? So basically, they're technically not exactly the same areas, but what's going on there is the same. If this red area converges, if that limit exists, then the sum of the black boxes would have to converge. In this case, the red area isn't finite. Mm-hmm.
But on that case, when the area under the curve has to be the same as the series plus 1?
Huh. Let's see. In this case, the first term is the same as the first term over there. The area of this box is 1. But when I go over to 2, I'm going to get not 1/2, but 1/4. So it's gonna drop. So the next term is a lot smaller than that one. This third term is an area of 1/3, but here it's going to be 1/9. And the claim is that if you use the integral test, you're not really finding the area of these rectangles. You're finding the area of this region right here. And it turns out that in this case, the area is finite. If I remember, I think it's actually 1. I think. We have to go through the steps to see what it actually is. But because that's finite, then the area of the boxes would have to also be finite. Right? And that's the idea. So there's that's kind of like I kind of told you the integral test, but this gives a little, the pictures kind of might make it more convincing, right? It sheds some light on some of the inspiration for it, right? Mm-hmm. What I'm representing here is really the sequence. What I'm really representing here is the sequence, actually.
Right.
So If I wanted to represent the series, it would be the sum. Yeah, exactly. For example, if I wanted to do like this right here, without the limit, this is analogous to the sequence of partial sums, right? If I was to define a new function, right, I'll call capital F as a function of x. I'm going to call it the area from 1 to x. I better not use x here for the integration variable, so I'll just say 1 over t dt. All right? And what that represents is that the area from 1 up to a certain point, right? So yeah, so you can see how, so this right here is this blue line is the graph of little f. If I was to graph big F, what it would look like is more like this. Actually, at 1, yeah, that's right. Actually, it literally is the log function, actually.
Oh, well, yeah.
Right? And it makes sense because as you add on more and more terms, it keeps the sum keeps getting bigger, but at a decreasing rate. And so the shape kind of agrees with that. This is where big F of x, right? Over here, right? Yeah. Over here, I can define a new function called big F. No, big, yeah, I called it F, right? Yeah, all right, sure. Big G of x is going to be the integral from 1 to x of 1 over t squared dt. Right? And I believe if you graph this, it's going to look something like but it's going to have a horizontal asymptote right here. You see, just like that graph right there, it's increasing pretty rapidly at first, but because the additional terms are getting smaller, the rate at which it increases is decreasing.
And that is where it converges.
Yeah. Yeah.
Wow, this one doesn't have an asymptote.
Mm-hmm.
It diverges.
So because this doesn't have an asymptote, it diverges.
That's good enough. We're good enough.
Yeah. When you evaluate this limit and you get 1, it means it has a horizontal asymptote at 1.
And then, like you said earlier, that variable
Mm-hmm. Yeah. Yep.
I'm telling you, I do graphically, and like for the last 2 terms, I did nothing but
Mm-hmm.
written, and I'm like,
Especially this class. I was talking with Josh earlier, like it's like this class that in differential and integral calculus, like for almost, I think every single problem, there's a picture you can draw. But here is kind of, a lot of times, like the only reason I can draw a picture for this is because I'm using the integral test. You know what I mean? Otherwise, I wouldn't be able to draw this picture, you know? So it is hard to kind of visualize a lot of these. If you were to write out a few terms, if ever this notation gets too confusing, you can get grounded by just computing some numbers. If n equals 1, I have a positive 1 over 1. If n equals 2, that's going to become a negative 1 over 2. If n equals 3, yep. After you do a few calculations, you might pick up on the pattern. And you don't really have to be thinking about the computations anymore. Right? So there it is. It turns out that this series converges. Yeah. Yeah.
Constantly subtracting from
Mm-hmm.
the addition.
Mm-hmm. Mm-hmm. Yeah, so basically, whenever, right, I'll summarize it by saying this. And this is another test, right? So if an is greater than 0 and converges to 0, then the series converges. Right?
I'm sorry. And what?
So basically, as long as I know, so this is the general form of an alternating series. If I know that that these terms are getting closer and closer to 0, then I can safely say that it converges.
To the same, to 0?
Mm-hmm. Yeah.
No, I mean the series converges to 0?
No.
This is going to go to 0?
No. It does converge. It doesn't go to 0.
1/4?
It doesn't go to 1/4 either.
Something smaller than 1/2.
We'll see what it adds up to in chapter 6. It turns out it equals
What?
natural log 2. Yeah. Yeah, that's it's pretty wild. Yeah. So yeah, it is kind of curious because, like, notice that 1 is a rational number. If you subtract 1/2 from 1, you get 1/2, which is also a rational number. If you add 1/3 to 1/2, you get 5/6, which is also a rational number. If you take 5/6 minus 1/4, well, you get something that's rational. The sequence of partial sums is consistently rational numbers, but it's a sequence of rational numbers that's getting closer and closer to an irrational number, right? That's pretty crazy. I'm pretty sure it's irrational. It seems like it's irrational. So, yeah, this is the big result. This is basically the only result, the new test you have to learn from this chapter. I think it's the only one, actually. Yeah, this is the only test that you have from this chapter. So good news, everyone. Just from this section, I should say. Yeah, pardon me. Yeah, we'll call it the alternating series test, right? However, it does have some other complexities to look at, such as what? We want to be able to kind of estimate if you're adding terms along the way. I'd like to know like how good my estimate is. I'd also like to, so we're going to have something analogous to the remainder theorem that we saw before for the integral tests, right? We were able to get bounds on the remainder, right? And so you can stop adding at some point. Like if I wanted to just stop here, just stop at 1/5, I could figure out, and if we're not in chapter 6 and we don't know that it equals natural log 2, then I just have an estimate. I'd like to know how close I am to the actual answer, right? The remainder theorem will tell us that. And some vocabulary. If you have a series that converges, but if I drop the plus or minus, it diverges, we would say it's conditionally convergent. Okay?
I'm sorry, can you say that again?
I'll do better. I'll write it down. So definition, right? So if let me write it like this. If the series AN converges, but the series of absolute value AN diverges, right? Then we're gonna describe the way in which this converges by saying AN is conditionally convergent. So it's conditionally convergent. Meaning, and I guess you can kind of see why. You know, here it converges, but in this mutation of it doesn't converge, right? And I guess one thing I should remark, I've been talking about AN here and here under the assumption that it's positive. Here, this is only a meaningful definition if AN itself could be alternating itself. So these are not necessarily just positive terms, right? This is only meaningful when you're dealing with an alternating series, okay? So this example, the alternating harmonic series, this is conditionally convergent because if I took the absolute value of each term and then added it up, it would diverge. But on the other hand, if you have a series that converges and the sum of the absolute values of the terms also converges, well, that means it's kind of, so like, I think a better definition, if I was to name it, I would say it's barely convergent. And this one's like definitely convergent, you know what I mean? But the term that they use here is really strong. It says, then we say that the series is absolutely convergent. So we have vocabulary for convergent series that describes the nature of that convergence. Okay? When we get to chapter 6, we are going to be concerned exclusively with absolutely convergent series. Yeah?
Quick question. So you, like in trig, everything was in terms of cosine?
Mm-hmm.
It's like, oh, it was like,
Yep.
was this everything in terms of being convergent?
Yeah. Yeah. I mean, that's the big question in chapters 5 and 6. Is it convergent or not? And more importantly, why? Yeah. Yeah. So this is an example of a series that's conditionally convergent. Can you think of one that's absolutely convergent? An alternating series that's absolutely convergent?
Maybe 1 raised to the n times 1 over x squared.
X. I don't want to bring in an x yet.
N squared.
Uh-huh. Okay. So that sounds better.
Why? And what's the big deal? Why can't we use n when we write down a series?
You can. It's I think the general convention, at least in America, is if I write the letter X, it's implied that it's like it could be anything. Like it could be a decimal, could be a fraction.
Oh, and then n, we're talking about integers.
Strictly integers. Yeah. I would never be plugging in 1.5 in for n, right? So. So yeah, you said it. I think that's what you said, right?
I just said -1 to the n.
That's what I was going to say.
I didn't say that.
Oh yeah. Well, it's all good. Yeah, that's fine. It's just the first term will be negative. No big deal, right? So in this case, right, that would be -1 plus 1/4 minus 1/9 plus 1/16 minus ... So we're adding reciprocals of squares. Well, we're adding and subtracting, right? Reciprocals of squares. Now, because this goes to 0, I'm not even using the p-series test now. I'm using alternating series tests. Because this goes to 0, the sequence goes to 0. I know by the alternating series tests that this will converge. So this converges by the alternating series test. I guess you could say AST for short. Moreover, since the absolute value of this, all the negatives are going to drop out, basically. In other words, you get this. Since this converges, right, by the p-series test, right? Since the absolute value also converges, I can now say furthermore, since this converges, the absolute value, it follows then that the original one without the absolute value, squared, converges. Oh, I guess I'm saying it a little differently. Absolute convergent converges absolutely. Means the same thing. All right? So this is an absolutely convergent series. I think I was thinking about this class yesterday, and I realized I think probably one of the biggest motivations for this is if I was to think of an overarching theme for this whole class, at least for the first half of the class, is weird things happen at infinity.
Yeah.
Weird things happen at infinity. And that's why we have this language to use, and that's why I'm more concerned with things that are absolutely convergent in Chapter 6. It's because when things are absolutely convergent, I can do things to the series that I'd like to do. In Chapter 6, the series are going to actually be a series not of numbers, but of functions. Yeah, continuous functions, right? And yeah, it's pretty crazy. But I can do things like take the derivatives of those functions. Like I'm taking the derivative of infinitely many functions. Or I can integrate infinitely many functions. Or even like this, something like this that you might take for granted, like with addition, you can rearrange the order of the addition, no problem. If it's absolutely convergent, it's okay, you can do that. But if you have a series that's conditionally convergent, weird things happen. Yeah. In fact, I'll just say, they actually mention it in the book, and I'm just going to mention it without proof, mostly because I'm not sure how I'd prove it. But it turns out that for any conditionally convergent series, right, it's possible to rearrange the terms to get literally any number you want.
What?
Yeah, it's weird. So like this one right here, this is conditionally convergent, right?
Right.
And I told you without proof that it adds up to natural log 2. But if I rearrange the order, I'm not going to change the signs of any of these. I'm not going to change the values of any of these. I'm just going to change the order in which I add them up. I can make it add up to like 5 if I wanted to. I can make it add up to.
We're gonna know how to do that.
I can add up to like 1 million, you know?
That's what's up.
Yeah, that would be kind of a.
That's what's up. I know how to manipulate math data. Okay.
Yeah, that's
You're
what's
going
up.
to jail.
Yeah. Yeah, I think that would be considered a paradox, right? And so we don't really want to deal with things like that. But it is kind of interesting, you could rearrange it. So in the book, they give you an example where they actually do rearrange it to add up to something else. They show you how to do that.
Yeah, there you go.
So. All right, so 5.2, huh?
That's the last question, number 137.
Oh, wow. 137. Oh, 5.2. Oh, shoot. Oh, that's good. Nice. The Sierpinski gasket. showing a picture of a Sierpinski gasket. This is an example of a fractal.
What?
Fractal. You ever heard of a fractal before? These are objects that are, there's a lot of things that are described as being self-same. Self-same, meaning, embedded within the object is a copy of itself. Like I think I saw a YouTube video where the guy had like this thing of broccoli, you know what I mean? And then he pinches off like a piece, and he looks at the little one, and it's like, it kind of looks like, if you look at it, it seems like it's just a smaller version of the original. So like the original is really just a bunch of copies of itself in a smaller form. That's an example of a fractal. Fractal, yeah. This picture right here, this is the Sierpinski gasket. This is also an example of a fractal because in this shape, notice if I was to just look at this shape right here, this piece of the shape, right? What you see in here is a miniature version of the whole. Isn't that interesting? And likewise here, 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 here. So the Sierpinski gasket contains within it 8 copies of itself. Right? So that's kind of cool. Yeah. Yeah, that's what, actually that's part of what makes it a fractal. Actually, with a broccoli, there's kind of a limit. When you have a chunk, you can break off another little piece. And it's like, oh, there's a copy there, but you get to a point where it's just like one little bud, and that's it. You know what I mean? A fractal is kind of more of a theoretical idea. So a broccoli isn't a perfect example, but yeah, theoretically, and even this is just a representation of it. Mm-hmm. But yeah, the way you construct a Sierpinski gasket is what you would do is you would start off with like a square, divide it into, draw 2 vertical lines, 2 horizontal lines, and just remove the middle 1/9 of it. You know what I mean? But then for each of these remaining 8 regions, you do the same thing. You divide each of these up into 9 sections and remove the middle 1/9. Same thing here, same thing here, 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 here. And then in each of these, there's going to be 9 little squares. At that point, they're solid, but you're going to do the same thing. Right? So I removed 1, and then I removed, 8 more? And then for each of these 8, I removed 8 more, so it's like 64. There's like 64 of these, if you count them all up. And then these little dots are the middle third of those. But even around each of these little dots, there should be 8 regions. And I can't see it on the picture right now. But theoretically, you would keep doing this forever. And that's how you construct a Sierpinski gasket. And it's just repeating what I just said, right? And after 4 iterations, compute the total area removed after n stages and compute the length of the total perimeter of the remaining set after n stages. Wow.
Yes,
This is the type of question I wouldn't ask on an exam because, that you have to think on your toes a lot. But that might be good for a take-home exam.
yeah, I just need to know how to set it up without actually.
Yeah.
Because if I was to do the area of this, I would be
Yeah, so let's see here.
I would try to get the area of the little white boxes and just try to set up the area of the big black box.
I think it might be, I think one way to attack this is to just do it in stages, right? So in stage 1, the area, let's just say, did they give the dimensions? They probably just said it's a square unit.
Yeah, let's just say 3 by 3 because you said nice and that made it understandable.
Yeah. Well, eventually we're going to have to start breaking up into fractions. You know what I mean? So I'm just going to call it a 1 by 1. All right? It's like, we're going to have to go there eventually anyway, so, So yeah, so the area, and also because the area is easy, The area is 1. At stage 1, the area is 1. So in fact, instead of writing a equals 1, I'm going to say the area a sub 1 is 1, right? But at stage 2, I'm going to remove, kind of draw these guidelines, you know, so that I can remove the middle third. And I guess to make it clear which part is included in the area, I'll go ahead and kind of shade in the region I'm talking about. So now what I have is that. And so the area at stage 2 would be 1 minus, I guess there's a couple ways you could do it. You could find the area of this guy and multiply it by 8, or just find the area of this guy and subtract it from 1. Should give you the same answer either way, right? I'm going to say 1 minus, since the side length of this is 1/3 and 1/3, right? And that would have to be 1/3 times 1/9, right? I'm going to leave it like this, though. Just because I suspect it'll make it easier for me to see the pattern down the road. Yeah. I've done these kinds of things before. I know how they go. And by the way, while I'm at it, since they are asking about the total perimeter, right, I might as well take note of the perimeter at each stage. Here, so the perimeter at stage 1 is all 4 sides, so that's going to be 4. But the perimeter at stage 2 yeah.
Plus 4/9.
Yeah. Well, no. Because the distance from here to here is not 1/9. It's 1/3, right?
Oh, yeah.
Not to be confused with the area, right? So the distance is 1/3, so the distance all the way around here would be 4/3. Yeah, 1 1/3, sure.
So I like just keeping fraction.
Yeah. So at stage 3, after I remove the middle third, I got to remove the middle third of each of these sections now. And well, I guess you get the idea. So I'll just draw it like this. I'll draw like a little box like that, that, and that, and that, and that, and that, and that. And this big one right here. So I'd like to know what is the area at stage 3 and the perimeter at stage 3. I guess I really should be shading in, to make it clear, I should be shading in all the regions between all these squares. But I'm going to vouch not to, just so that it doesn't get too messy, you know. There's always these artistic considerations when you're doing mathematics too. Because the whole point of the picture is to make it clear. So as long as it's clear what region I'm talking about, then the area would be what?
1 minus 1/3 squared minus.
Mm-hmm. Yeah. So
1/9 squared.
notice that this kind of notice that the pattern we're observing really lends itself to a recursive definition. You're really just taking the previous answer, right? That's a recursive pattern. But yeah, but at the same time, let's just leave it like this. So that's the previous area, but then we're going to be subtracting from it how many? 8 of these, minus 8 of these squares, each one having an area of, well, if this right here is 1/3,
So that's 1/9.
yeah, it's 1/3 of 1/3, right? That means that this right here is 1/3 of 1/3, namely 1/9. So yeah, but the area of it is not 1/9. The side length is 1/9. So it's going to be How do I want to say this? 1/9 squared. I was debating in my mind whether I should say 1/3 squared. I'll change the other notation if it helps, you know. But that's the area, right? And likewise, the perimeter is going to be our previous perimeter. Well,
4/9.
No, so that's still a third plus a ninth.
I'm thinking there's 8 of them to begin with, right? There's 8 of them. And each one has a perimeter of 4/9, right? Because each one is a not 1/9 by 1/9 by 1/9 by 1/9. So 4/9, I'll say. 4 times 1/9, which is 4/9. And there's 8 of them, right? And you just keep doing what I'm doing until you see a pattern.
I'm not really seeing a pattern, but so the next perimeter would be plus 12.
Could be. Yeah, I think we're, at this stage, I think we're right on the cusp of starting to see some stuff. Like, I think it's pretty clear to me that the next one's going to have another minus, and the next one's going to have another plus. But it is curious that this 8 kind of popped out of nowhere. I can see there's consistently a 4 here, but this 8 popped out of nowhere, it seems.
I'm sorry. There is 8 of the small ones, the third
Uh-huh.
squared. So that 8 times 8 of those, 64
Mm.
times whatever that is, whatever the area or perimeter is.
Mm-hmm.
Which should be a 27, right?
4 27s.
You lost me.
We're saying
What?
the perimeter, the next one is going to be plus 68 times 427.
Oh, I see what you're saying. Yeah, right. Because
64 times.
there's going to be 8. Each of these 8 is going to have 8. So 8 times 8 is 64. So the next one's going to have a 64, and then it's going to be with a 4. 27, sir.
Or it would be 81st.
Yeah, one of the two.
Yeah.
Maybe 27s.
Because it would be 1/3 of 1/9, which would be 27. Oh yeah, you're right. Yeah, so it would be 27. So it would be 64 times 4 27ths. Whereas the area is going to be minus 64 times 1 over.
27 squared.
Yeah. Yeah, because it would be 1/3 of this would be 20 over 27 squared. Yeah. Yeah. Interesting. So I think if you write that out, what we just said, if you write it out, I'm going to leave it for you to finish. But if you write that out, what we just said, I think the pattern's going to start to jump out at you, and I would be on the lookout for a geometric series.
Yeah.
You know.
Because you went with.
Yeah, but I'm not tracking with the big, like with the 8.
Mm-hmm.
How does that fit into geometric series? Like,
Mm.
but if I say my R is 1 over 3 squared,
So you're saying A4 can be 1 minus 1 over 3 squared minus 8 over 9 squared minus 64. Maybe I should leave it as 8 squared. How about that? Over, what did we say?
27 squared.
27 squared?
Oh, but it's supposed to be 8 squared times 4.
Oh yeah, times. In the bottom one.
Oh, okay. Oh, yeah, there.
So 4
The
minus.
middle one should still be the second term, the third term.
Mm-hmm. So 8.
Okay, 1, 2, 3. Okay.
Interesting.
Right. So,
There's a 4 in all of them, so you can factor that out.
That's a good idea.
For the PM, sorry.
yeah, for the 8.
Mm-hmm. Well, I guess it's going to be is it geometric? That's the big question.
Yeah, because
It's,
Because geometric, you'd be multiplying. The bottom is still squared.
yeah. Yeah, like from here to here, I'm multiplying by a third to get here.
Right.
But from here to here, I'd have to multiply by 8/3.
is that a 3 on that?
Is that a
3 to the third?
Is that a 3
Because right above that, that says cube.
Oh, yeah.
So that's squared.
Yep.
Okay.
But at least this one is this times 8/3.
That one.
And I'm pretty sure the next one would also be this times 8/3.
So what we do wrong in the first term?
So technically, this is not a geometric series, but from this point forward, it is.
So you can just solve that and then add.
I would probably like set the 4 aside because that's kind of like an exceptional case, right? But for the rest of it, I would write it like this: 4/3 times 1 plus 8/3 plus 8/3 squared. And I think it's just going to keep going like that. That would be a geometric series.
So you would do the same thing on the top one.
Yeah, maybe,
Oh,
if it
how
works.
does-
Yeah, now,
How does that equal out though? 4/3.
No, that's true. Look at that. 8/3 is bigger than 1.
I'm confused now.
Well, we talked about it. It just means it doesn't converge.
Oh, yeah.
So
Oh,
This
yeah.
section.
if you go out to infinity, the total perimeter would be infinite. You'd have infinite perimeter
Oh,
in
yeah,
this,
perimeter, yeah.
contained in that shape, right?
What about the area?
So this is infinite. Yeah, but this one may or may not be infinite,
But
right?
3 is something of this. So 3 cubed is 27.
Yes.
3 squared is 9.
Mm-hmm, mm-hmm.
So it's really 3 to the n raised to the freaking square, right?
Mm-hmm. Right.
Not necessarily, we don't, it could just be times.
Right, let's leave it there.
No, because the fourth term could be 27 times 3, not 27.
Yeah, maybe I should think of it.
The next,
Maybe I should write it like this then, since the square is what's in common. It's -1/9 minus 8
8 firsts.
over 9 squared minus 8 squared over 9 cubed.
Yeah, what's up with this 8?
Yeah. I think these first 2 terms are going to be exception to the rule. But from this point forward, it looks like it's geometric. And moreover, I think it's going to be geometric with, because in each case I'm multiplying by 8/9, which is less than 1.
And the first one is always going to, the first 2 terms wouldn't matter because you could start at the same time, right?
Exactly.
If it's infinite.
Yeah.
You don't know where you're starting.
So this is kind of leading up to a curious fact that this fractal, the perimeter is infinite, but the area is finite. Right?
Doesn't make sense because
Yeah.
as the perimeter gets bigger,
Mm-hmm.
the area gets smaller.
True. Oh yeah, that's true. The areas are getting smaller.
But then why
Yeah.
wouldn't the area be 0 if the perimeter is infinite?
Well, what's happening?
Because
It's getting smaller, but it has like an asymptote. So I got going like this.
that's where conversion got started.
All right. Well, let's see. Yeah, that's an interesting problem. Kind of makes you think.
I still don't think we answered. Oh no, we're supposed to write the equation.
Yeah, I was kind of leaving something for you to do, but yeah, I would be kind of curious. The answer should be less than 1, right? It should be less than that,
Has to be. Yeah.
right? So yeah, I'm kind of curious. Is it going to be like 1/2, 1/3? You know? So you can figure that
So
out
if you
though.
graph